Welcome back to AM. Dr. Bill Deese from Louisiana Tech joins us now from the chemistry department at Louisiana Tech.
That's right.
And I don't want to be a weenie about this, but the last time you brought hydrogen gas, you nearly blew my brains out.
Well, that was a very popular segment, Dave.
Yes, it was with everybody.
When you exploded the hydrogen balloon.
Yeah.
Okay. And I explode a lot of hydrogen balloons in my classes, and I do it for programs I do for school groups, elementary school groups. And people have been writing me and calling me, and they want to know, when are you going to have hydrogen back on the show?
Yeah.
Okay. And so I thought we'd show something, property of hydrogen gas today that does not involve flame. Okay.
You did bring the goggles.
But we do need to wear our goggles. Anytime you use a compressed gas cylinder, you should have eye protection on.
I agree.
Okay? And so we're going to put our goggles on.
I wish I had an asbestos suit just in case.
Well, everything will be fine. We're actually going to have a very small amount of
Beam me
hydrogen
up, Scotty.
gas here.
Okay.
All right. Now, one property of hydrogen, in addition to it being flammable.
Do I look as goofy in these goggles as you do?
I think you look great, Dave.
Okay, thank you. Go ahead.
Do I look goofy?
Yeah.
You said I look goofy?
Look like Kermit the Frog, but other than that, you look fine. Now, what are we doing?
Well, okay, one property of hydrogen is that it's the lightest gas we have.
The lightest gas.
It's the best gas to use if you're going to lift something off the ground with it.
Balloon, big balloons.
Okay, as far as lifting a lot of weight. Now, we don't use hydrogen in airships anymore because it's flammable. Okay.
The Hindenburg showed us that. Did that have hydrogen in it?
Yes, the Hindenburg had hydrogen gas in it. Yeah. Now we put helium in the airships because it's not flammable. Okay, now what I have here is an apparatus that has a bent glass tube, and that tube goes down below the level of this blue water. Okay.
Tube goes to the bottom of the beaker.
Yeah. Now the rubber.
This is just water. This is acid.
It's just water. Well, the rubber hose is connected to a glass tube, and it only comes down just below the stopper.
Okay, so
we have an area of air here, and then just liquid water.
Okay.
Now this is connected to an unglazed ceramic cup, and that ceramic cup, since it's unglazed, it means it's porous.
Porous.
Okay. And if you put water in that, water would slowly seep through it. Okay?
Osmosis.
Yeah. Well, no, it would just seep through the holes. Okay.
Seepmosis.
Osmosis is a little bit different thing.
Right.
All right. And so now gases can also go through those pores in that cup.
Okay.
Okay. And so we're going to be using that in a minute. Now, what I want to do is fill this container with hydrogen gas.
But it's light.
Okay. Well, all right. That's a good point. So if you hold that like this, and we were to let the hydrogen escape, it's just going to go up to the top of the studio. So instead of filling the beaker up with hydrogen, what are we going to do?
Turn it over.
Okay, invert it, and we're going to fill it down with hydrogen.
Okay.
Now, hydrogen is invisible, so how are we going to know it's completely filled down?
When I start to float up.
Well, okay, or the beaker will quit getting lighter, right?
Okay, right. Yeah.
But you won't be able to tell. It's such a slight difference.
Okay.
But we'll be able to hear it fill down.
Okay.
And if you'll hold it up a little closer to your microphone, maybe we'll be able to hear.
No explosion.
No explosion.
No explosion.
There's no matches going on in here. Okay, here we go with hydrogen gas.
Okay, I hear it.
Okay. I can't hear that.
I can hear it.
Okay. It's not as loud as I expected, but you can hear the pitch of that sound changing, and now the beaker is probably filled with hydrogen. Can you feel the gas going by your hand?
Yeah, I feel it going by my hand.
Okay, so now
right
the beaker's underflowing now,
okay.
right?
Okay, but it's this part, yeah, right. This part is full of hydrogen.
We hope so, or I hope so. All right, now if we hold it like this.
I don't turn it
over. Okay, now what I'm going to do is to surround this ceramic cup, this porous ceramic cup, with an atmosphere of hydrogen.
Okay.
Okay, and let's see if anything happens.
Woo, look at that. Now, wait a minute. The hydrogen, explain what happened. This thing is throwing water off. Look at that. Tell us how that's working.
Well, what's happening? Obviously, the pressure is increasing inside the flask, right? Okay. And that's forcing the water out.
Right.
And now slowly the pressure is dropping, and now it's back down to about atmospheric pressure, right?
All right, we got about 30 seconds.
30 seconds. Okay, now
can
I get a close-up of the flask down here? Watch what happens when I remove the beaker and expose this ceramic cup to the air again. It pulls bubbles back through. It pulls air back through. Okay, so now the pressure has dropped inside the flask. All right. Now, what's happened here is before we immerse the ceramic cup in an atmosphere of hydrogen, air is going in and out of the cup at the same time.
Okay.
And when we surround the outside by hydrogen, more hydrogen gas goes in than air comes out. That was obvious because the pressure went up.
Went up in here.
And then when we remove the hydrogen atmosphere, the opposite occurred. Now, the only way you can explain that is to talk about molecules. The air is made of molecules. Hydrogen gas is formed by molecules, or made of molecules. And they're at the same temperature. They have the same kinetic energy, so that must mean that the hydrogen molecules are moving faster than the air molecules. And we know the hydrogen molecules are much lighter than air because hydrogen floats in air. And so I love doing this demonstration for my classes because you cannot explain it without talking about molecules and that small ones move faster than big ones.
I think the goggles make us smarter. Thanks for showing that. Very interesting. Another great scientific experiment, easily done and easily explained.
What we've done is demonstrated kinetic molecular theory.
Okay, I can put that on my resume. We're going to take a break. We'll be right back.